In this video, we'll be talking about particle motion, but this time in terms of integration. So previously, we have learned different facts about particle motion that involves derivatives and differentiation. Below are some new facts about particle motion, but these incorporate integration. So first we have net change or displacement. That's basically change in position. That can be found by the integral from a to b of the velocity function. Total distance traveled over the closed interval a to b can be found by a very similar integral, except this time we're looking for the absolute value of velocity. If we just think about the difference for a second about between displacement and total distance, let's imagine that you drive a certain route from home to school, and then you drive that same route backwards. You go from school to home at the end of the day. Your displacement is 0. That means your position did not change, right? Where you started and where you ended up are the same. So therefore, your net change or displacement would be 0. However, your total distance traveled is not 0, right? You traveled however many miles to school and however many miles back home. So that should always be a positive value, hence the absolute value bars. Then finally, we're also going to be talking about how to find a position at a given time. So for that, we're going to use our initial condition that will be given to us in the problem, plus the net change, essentially, the integral from a to b of the velocity function. So again, just a note, total distance traveled and displacement are not always equal. When you are finding total distance algebraically and you're not using a calculator to evaluate an integral, we want to always be mindful of any times where the particle might change directions. All right, let's take a look at question 1. So question 1 says an object is dropped off the top of a 500-foot building. If the velocity of the object is represented by v of t equals negative 32t plus 6, we're going to write a function that represents the position of the object, and we're going to write a function that represents the acceleration of the object. So I'm just going to set up two little sections here. So one where we find the position and one where we find the acceleration. So I'm actually going to do these in reverse order. Acceleration, we know from derivatives and learning previously that acceleration is basically the derivative of velocity. So I can very quickly determine that that is negative 32. Position now, though, now that we know how to essentially work backwards and find an original function through integration, we are going to essentially be looking for the integral, the antiderivative of that velocity function. So what I'm going to do, I'm going to use s of t to represent the position. X of t would also be another common notation. And I'm going to essentially reverse or undo the power rule. And I'm going to add 1 to the exponent and divide by that value. The same thing with the 6. And then I would get plus c in here. Now, c is our constant that goes at the end when we are integrating. And in this case here, since we have a polynomial function, that's really looking for our initial value. So we know the object is dropped off the top of a 500-foot building. So this tells me that I can clean this equation up to negative 16t squared plus 6t plus 500. And now we have our position function and our acceleration function. Number 2, an object is moving in a straight line. Its velocity can be represented by v of t equals the square root of 5t plus 4 meters per second, where t is in seconds. The object has an initial position of x of 0 is equal to negative 2, and we're going to figure out what the object's position is at t equals 8 seconds. So in order to find a given position, what we basically want to do, so we're going to be looking for the position at 8, so I'm going to say x of 8. We want to use our formula. If I just scroll back for a second here, we have to think about it as like, where did we start? Where did the particle or the object start? Where is its initial condition? And then basically, how did it change? So we know that at x of 0, we are starting at negative 2. And we're going to be adding basically how it changed. So it changed from 0 to 8 seconds. So keep in mind, just to note here, whatever your initial condition is should match and correspond with this bottom bound, the lower bound of the integral. And then I'm going to put in our velocity function, so 5t plus 4 dt. All right, so if I evaluate this, because we want to figure out what x of 8 is, so I'm going to have to integrate here. When I do that, I'm going to imagine that we have a 5 here, and I'm going to think about this being basically an application of the chain rule, which means that we're going to balance that out with a 1/5 in front. Just as a side note, the square root of 5t plus 4, just remember that's the same thing as 5t plus 4 to the 1/2 power. So I'm going to be using that to help me integrate. So now simplifying this a bit, I'm going to copy down the 1/5. And now I'm going to find the antiderivative of the square root of 5t plus 4. That means that I'm going to take 5t plus 4, add 1 to the exponent, and I'm going to multiply by that reciprocal. I could also divide by 3/2, but in the end, that's going to be multiplying by the reciprocal anyway. And we're going to be evaluating that integral from 0 to 8. All right, if we would like, we could clean this up a little bit before we actually evaluate. So this looks like I have 2/15, 5t plus 4 to the 3/2, and we're going to evaluate that from 0 to 8. And so now that I have this, I'm going to basically plug in my upper bound. This is, again, using the fundamental theorem of calculus. I'm going to plug in my lower bound. I'm actually going to change that t to a 0 here. And when I evaluate this, this will give me the object's position at t equals 8 seconds. So when I simplified this using my calculator, I got that the object's position is 35.848 when we round to 3 decimal places. All right, number 3, a particle's velocity along a straight line is given by v of t equals 4 sine t. Find the particle's displacement on the interval 0 to 2 pi. Then find the total distance traveled over the same interval. All right, so let's start with displacement here. So displacement, our bounds are 0 to 2 pi, that's given to us, and we said displacement can be found by integrating the velocity function. So by integrating 4 sine t in this case, dt. All right, when I take the antiderivative, I'm going to get negative 4 cosine t and evaluate that from 0 to 2 pi. And now I'm going to plug in my bounds using, again, that fundamental theorem of calculus that we saw in the previous problem. And when I simplify all this, I'm going to get 0. In order to evaluate cosine of 0, cosine 2 pi, if we do not have our calculators, one way to do that is by thinking about the unit circle. 0 and 2 pi are both over here, and we can see that the x value at those coordinates is 1. Now, for this question here, when we are finding displacement, we could also verify this answer of 0 graphically if we think about what 4 sine t looks like, or just any sine curve, like sine of x, for instance. Okay, we can imagine that it looks like this, and this value here is pi, 0, 2 pi. So since the amount of area above the x-axis is equal to the amount of area below the x-axis, that net change, that displacement essentially is going to give us 0. But again, we talked about in the beginning of this video that displacement and total distance are not necessarily equal to each other. They can be, but in this case, they're not. So in order to figure out total distance, so I'm going to separate that and put all that work over here. If we have our calculator available to us, then yes, we could just evaluate 0 to 2 pi of the absolute value of 4 sine t dt, right? We can put that in our calculator. But let's say that we don't have a calculator and we have to do all of this by hand. What we're going to need to do first is figure out where does it change position. So I'm going to put that work in here. Basically, in order to do that, going back to rules we learned earlier in the year, we know that a particle changes position when its velocity is 0. So if I solve this, and again, I can use my unit circle to help me get these values, or this one value, I'm going to get that t equals pi. So sine of pi is equal to 0. So in this case, we know the particle changes direction at pi. So what I would have to do is take our initial integral from 0 to 2 pi and break it into two new integrals. So from 0 to pi for sine t dt. And then we're going to do the same integral, but this time from pi to 2 pi. And we are going to make sure that we find the absolute value of all of these. So in the end, when I evaluate this, here I'm going to get -4 cosine t. We're going to evaluate from pi 0 to pi. And then same thing over here for the antiderivative, but this time evaluating from pi to 2 pi. And when I sit here and do this using the fundamental theorem of calculus, plugging in the bounds and so on, and also knowing that we need these values to be positive, we are going to get 16 as our answer. So let's talk about something just to make sense of that answer for a second. If I go back to this sketch from before, what this is basically saying is that the area here is 8. This area is -8. Now, we know area can't really be negative, but that negative in front really represents the fact that it's below the axis. So if we think about that in terms of absolute value, we're really doing 8 plus 8 and getting 16. Also, just take note where we found where the particle or the object changes direction was at pi. We found that algebraically over here, but just knowing what a sine curve looks like, we could have gotten our answer that way too. All right, let's take a look at one last example involving motion and integration. So a particle's velocity is given by v of t equals -t squared plus 3t plus 4. T is in minutes, v of t is in meters per minute. Let s of t represent the particle's position. So part A says find the time where the particle achieves its maximum velocity. So whenever we're looking for maximum, or minimum for that matter, but this problem is maximum, that's really looking for an extrema. And if we think about how did we find extrema earlier in the year, that's basically asking ourselves, where does the derivative equal 0, right? If you think about the maximum of a curve, it has a horizontal tangent line, meaning the slope or the derivative is 0. So what we're going to do here is we are going to take the derivative of this function. So realize that the acceleration is the derivative of velocity. And when I do that, I get -2t plus 3, and we're going to set that equal to 0. So we're using our kind of optimization process from earlier in the year of setting the derivative equal to 0. And when I do that and solve, I will get my answer of t equals 3 over 2. Okay, so that's basically the x value of the vertex of the problem. All right, part B, the particle has an initial position of s of 0 equals 4. Determine the particle's position at t equals 2 minutes. All right, so we know our initial position is 4. We're going to set an integral from 0 to 2 of the velocity function. And now we are going to integrate and evaluate this. So I'm going to find the antiderivative of that expression there. So I'm going to have -t cubed over 3 plus 3t squared over 2 plus 4t. And I'm going to take that new expression, basically the antiderivative, and evaluate from 0 to 2. Okay, that means that we are going to be plugging in 2 as our upper bound here. Then we'll be subtracting what we get when we plug in our lower bound of 0. And you can even see here that we are going to get a lot of stuff here that essentially goes away, right? Because all of that is going to give me 0. So I'm going to go to my calculator to evaluate this, or I could sit and evaluate it by hand. But basically, I'm finding what we get when we plug 2 into that antiderivative. Okay. So when I do that in my calculator, I got 11.333, or if we're doing this as a fraction, 34/3, and we've got to add that initial 4 to it. So our answer here, let's do this with 3 decimal places, would be 15.333. All right, for part C, the last part here, it says determine the particle's total distance traveled over the interval 0 to 3. So just like we saw in question 3, we have to check to see where the particle changes direction. So that means we would be setting the velocity function equal to 0. So again, this work here, I'll zoom in a bit. This would tell me where the particle changes direction. So I'm going to divide out that negative first to make this easier to factor. I'm going to get t minus 4 and t plus 1 as my factors. And as my zeros, I'm going to get t equals 4 and t equals negative 1. So when we look at this here, and I zoom out a bit so we can see our interval, negative 1, t equals negative 1 can't happen because we can't have negative time. But we actually don't even need to consider t equals 4 because these are just not in the interval. So that means that we don't have to address anything about the particle changing direction. We can just go to our calculator essentially and evaluate this integral. So the integral from 0 to 3 of the velocity function. And we know that we're going to get positives all around when we do that. When we integrate this by hand, if we were doing this without a calculator, right, we already know what the antiderivative is from the previous problem or the previous part of this problem. I'm going to evaluate from 0 to 3. Just like in the previous part, when I plug in 0, we're going to get 0 there. So really the only part that is going to affect this problem is what we get when we plug in 3, and all of this will give us 16.5. And in this case, our unit would be meters, and that would be our total distance traveled over the interval 0 to 3.